Department of Education through two major grants to build the capacity of STEM within the Otero Junior College campus. So our initiatives are really geared towards enlightening our community, our faculty, and our students with different elements of science, technology, engineering, and mathematics. So today we've brought in an national speaker. His name is John Benoni. He's a physicist, has advanced degrees in chemistry and physics. Did working on his PhD in electrical engineering, wrapping that up. John also is an adjunct professor at several different colleges in eastern Tennessee, currently at Hiwassee College in Tennessee. He is also an amateur astronomer. I would say more than amateur. Worked in nuclear engineering and physics for quite a long time. Worked affiliated with NASA, helped me out here with this long list of organizations. But we want to give a warm welcome, thank him for coming, and we hope you all enjoy his lecture.
Thank you, Laurie, and everyone for coming here. It's my pleasure and privilege to be here. And in preparing for this lecture, I was challenged by the infinite number of extremely exciting topics to talk about, even from the list that was presented to me. And so we'll get to where we can, but I want this to be relaxed, open. I talk a lot, I talk fast, so you may have to talk fast to get into question. That's why we'll recognize you. Just raise your hand, and we'll try to make this a discussion and not just a lecture, okay? So let's hope everything works fine. Starting with this. Okay, so these are some of the things that we might talk about, but it shows, and I don't even have all my slides here for some of this. Some of these things are going to be just off the cuff, depending if we get there or not. But I certainly want to spend a good amount of time on the first two items listed here, because there seems to be a tremendous interest in exoplanets and its astronomy and the implications of astrobiology and astrochemistry. We might get to talk a little bit about the Standard Model and some neutrino physics, which is interesting. And of course, the black holes are always a popular topic, not just among the sixth graders, but among us big kids like me too. And so, and then of course, the recent announcement that after all there might some computer models show that there might indeed be that thing that I teach all my students don't exist, may very well exist after all, magnetic monopoles. And I assure you that whoever discovers them will win a Nobel Prize in Physics for it. That will not be me. So, okay, so that's the general lay. So I want to talk, before we can talk about exoplanets, we need to talk a little bit about our own planets, our own solar system and such. Is this in your way, dear? I'm sorry. Let me get this out of your way. Yeah, you bet. I'm just going to move this over here. And, all right. So how are planets formed? Okay. Well, we have, before we can know about planets, we have to know about stars. It's also interrelated, okay? So the cartoon, no, I'm not going to start off with the cartoon. I'm going to start off with the poem. Oh, with the poem. Yeah, didn't I tell you? Yeah, the other group. There's something passionate about poetry. So I am an emergent voice. I'm not established yet, which I define as being consistently published in the top tier journals. I can only periodically get in the top tier journals, but I have over 300 publications and 3 pushcart nominations, and so I take my poetry seriously too. So I'm going to start off with a little poem called "There's a Gold Twinkle in the Night," which is published in the Telescope. I remember my birth. My simple atoms and cold clouds of dust slowly swirled in outer space, but my cocoon was warmer at 10 degrees above absolute zero. A disturbance in another part of the galaxy swept through, and gravity cradled me until I incandesced to a ball of fire. I remember my life. My breath, strong, cleared the space around me. I could see the marbles move in circles, as if immobile above my crib, but hung on nothing. I grew in stature, becoming ravenous. My insides raged an inferno, consuming me until I bloated to a supergiant. I remember my death, jealous, the frigid crunch of gravity. Fires died, my iron-heavy heart stopped beating as I tore apart in convulsions. My atoms rendered to the deep blackness, to the stardust of my birth, my legacy, the scattering of stars, the genesis of suns, the transformation to gold. And that last line was inspired by Joni Mitchell's song sung by the great group, which some of you may not know, but some of you will. Crosby, Stills, Nash & Young. And the song was I Am Stardust, I Am Gold. I think that's the name of the song. And so that's it. Okay, so how about these sons? And yeah, our sun isn't going to exactly die out the way that I read it. In that poem, it was for really a big sun, not our little dwarf yellow sun. Our fate is going to be a little different. All right, so Laplace, the famous Laplace, who's the mathematician, and Kant, yes, that one, who's the philosopher. See, back then, men and women were Renaissance people, so they knew science and philosophy about equally as well. And it's exciting how both these fellas came up with an idea of how the solar system might have formed. And it starts out with what's called the solar nebula theory. And basically, you have a big old assembly of molecules and dust and gas out there called molecular clouds. It's a little warmer than the rest of the universe. The typical microwave background radiation tells us that the universe is about 3 degrees Kelvin, give or take a few tenths. But these molecular clouds need to be a little warmer, about 10 degrees Kelvin, maybe up to 30, not much more than that, I don't think, for the possibility of them coming together to form what will become our sun and our planets. And that is what starts it. I suggested in the poem, perhaps a disturbance from another part of the galaxy, a gravity wave coming through, sending a ripple. You know, when you see in the ocean, you see sargassum seaweed floating on the surface, and then a wave comes, and the seaweed tends to clump on the crest. Well, so too the gas and the dust can all kind of clump when the disturbance, a density wave, moves through. So you have a hot ball of gas, you have a ball of dust and gas, which is not hot at all, so at 10 degrees Kelvin, all right, just barely above absolute zero. And it's just barely moving, but it's held together by its own self-gravity. And then comes along a disturbance, and that's going to make things come a little closer for a moment. And of course, this gravity is such a strong force, the closer you get together, the much stronger it is, because it goes as 1 over r squared, all right? Then things start falling into each other. So there's a gravitational potential that gets energized, so to speak, and things fall into each other. So you trade the gravitational potential energy for kinetic energy. So what happens when if this was just pieces of cloud like that, if you slap your hands together, you'll get an idea. You notice a couple of things. We call them inelastic collisions. But you'll notice a couple of things. Your hand will sting. You'll feel a little warmth. Okay, that little warmth is exactly what happens. As things crash into each other, heat is generated, and that's important because this heat is going to eventually get so hot that the gas and dust will incandesce into a ball of fire, basically. We call it a proto-sun, something that's going to eventually become our own sun. All right. So, and they have fancy names, and in these dust cocoon is this glowing fire from which eventually all our entire solar system is formed. I'm going to show you a little film here in a minute, but what I want to say is this: something that's normally taught or not taught is that you have this spherical ball, approximately spherical ball of black gas and dust. Okay, as it comes together, it will be spherical. All right, what's going to happen is it's spinning slowly, and as it comes together, just like an ice skater does this number. I can't do it to my traffic because I'll get dizzy, and I'm just getting over vertigo. So, but the thing is, just by changing your shape, you can change how fast you spin. You change the shape of this slowly moving sphere, and as it gets smaller, it goes faster, and then you change the shape, its speed is going to change as well. It's a principle called conservation of angular momentum. And ice skaters know about that real well. But what we normally are taught is that this sphere of ball of gas and dust becomes a disk. Well, really, it's not quite true. It's mostly a disk, but there's still a pretty spherical bulge in the middle. And why would it become a disk anyway? As you take a sphere and you spin it faster and faster, it'll start to squash out into what's called a prolate or oblate, depending which direction you're looking at, spheroid. That doesn't look like a disk. Well, yeah, go ahead and squash that disk way on down. Yeah, okay, but it's kind of hokey. I don't buy it. I never bought it. I never bought the argument that just gravity is going to explain the sphere of the disk business. I think it's far more. Remember, this is hot, and we have the ionization of a bunch of material. So we have ions, and we also have some remnant of a magnetic field to begin with, as maybe a weak field. But there's another conservation law that normally isn't taught by a fellow whose name is Alfvén, A-L-V-E-N, with an accent. I think it's Swedish, I'm not sure. Alfvén had proposed that magnetic field lines in plasma remain frozen there. In other words, there's a conservation of magnetic field lines. So by changing the shape of something, all you do is basically concentrate that magnetic field. So there may be a weak magnetic field in the ball of dust and gas, but it concentrates a whole lot as it gets into the sun. So our sun has a magnetic field of about I don't know, 100 Gauss. Our magnetic field is a half a Gauss, and the Gauss is a pretty small number. It's like, what's a Gauss? 10 to the minus 4 Tesla or something like that to get light unit. So it's a small number. But okay, so where am I going with all this? I submit to you that it's the magnetic field that helps ultimately determine the shape of the disk. And I believe that as the ions are flowing in the disk, visualize my fingers as the direction of the electric field, the magnetic field coming basically out, up and around, looping around at the top. You have a magnetic field, electric field, and what's going to happen when you have particles moving across electric and magnetic field? They're going to drift perpendicular to it. So I think it's actually going to actually constrict and compact this bulb, this end, into a more disc-like shape. But that's just me. I mean, I may be totally wrong, but I don't think so. All right. Orion Nebula is one of these places where stars are formed. They're called stellar nurseries. And I like the Orion Nebula because you can go out here tonight and look at it with your naked eyeballs or binoculars and see this lovely thing. Now, you won't see all these colors, but it's there. And so what I want to show you now is a beautiful, these are real images that have been manipulated, like 20-some thousand images, that have been manipulated to produce a three-dimensional object, as if, and you're kind of like, not floating, but imagine yourself in a little spaceship just negotiating inside the Orion Nebula, okay? And this is what the folks in California did. Oh, by the way, what you see right here, you can see these 4 stars. They're called the trapezium. You can see them with binoculars pretty easily. All right? They're hot OB stars, and they're blowing. Remember I mentioned in the poem about like a breath blowing everything out? It's just tremendous outflows, and it clears the area. Now you're going to see these little potential solar systems form. Watch as we play. Well, you better listen, sucker. Okay, looking good. It'll be voice. It's 4 minutes. Where's the voice? Where's the voice?
Do we plug it in?
Yeah. Where's the voice? Here we go, here we go, here we go. Hold on. Okay. Hold on. Something happened. We're going to do it right. Come back here. I don't know why the volume defaulted to 0. That's what the problem was. Here we go.
Using volume visualization, we can investigate the 3D of the Orion Nebula. This nebula is an enormous cloud of dust and gas that is several light years across and 1,500 light years from Earth. The cloud glows from the light of 4 hot young stars at the heart of the nebula. Each star is thousands of times brighter than our sun. The center of the nebula is hung out by radiation from these central stars.
These little dust things, they're protoplanets.
Possessing a cloud called HS2, astronomers from Hubble Space Telescope images, a disk of dust and debris orbits the star. Astronomers believe this marks the birth of a system of planets. Each of these teardrop-shaped clouds is a blanket of gas and dust that surrounds a newborn star.
Those are real colors from the excited atoms that are in that gas. They emit visible light.
As we pull back and end our journey, we see the nebula from the viewpoint of Earth.
And you'll see that it's in the belt, the sword, and the hilt as well, a little below the sword and Orion. Is it going to show that? No. I might have another picture to show you, to remind you where to look. With your naked eye, you'll see a fuzzy spot there that is, and M42 is it's affectionately called as well. After Messier, that French guy who was looking for comets and got really packed and finding all these other things that were not comets. And so he named them so that people would, don't look at M42, that's not a comet. Don't look at M1, that's not a comet. That kind of thing. But he actually did a great service to us. Okay, so we have, so you visualize this gas. You saw all that ball of those little protoplanets and those gassy things. And in the heart of that is this hot glowing sun, or what's going to be a sun. It isn't a sun yet, okay, but it's a hot ball. All right, and what happens is that as it gets hotter and hotter, finally there's a point where the most ubiquitous element is hydrogen. Okay, so as you can light it up, you get the ball of gas, mostly a burning hydrogen. When hydrogen starts to fuse, and I'm talking about from a nuclear standpoint, when you fuse hydrogen, you produce helium, the next simplest element. All right, a tremendous amount of energy is given off. Why? Because of Einstein's understanding that matter can get converted to energy. So some of that matter seems to be missing, actually gets converted into a tremendous amount of energy. This is a source of fusion energy. And so now what happens is this ball of gas, and what that temperature you need that to happen is going to be somewhere around 15 million degrees. It may actually start a little sooner than that, but right now, if you were able to stick a thermometer, so to speak, inside the center of the sun, you see about 15 million degrees is what you find. On the outside, it's just a mere 6,000. You know, it's nothing. You know, it's just barely hot enough to go hot. So anyway, so as soon as this ball of gas, this proto-sun, starts fusing hydrogen, that's when it's officially a star. If it isn't fusing hydrogen, fusing something, it isn't a star. Now, we violate our own definitions, like with white dwarfs and things like that. But in general, when a star is born, for it to be born, it must be fusing. So these things called brown dwarfs aren't really stars. They're just failed stars. They're bigger than Jupiter's, but not quite big enough self-gravity to get that internal heating and all that compression. So that's what happens. So when a star is born, it's called a main sequence star, automatically. And what you see here is the outer temperature of the star, hotter to the left, and how bright it is up and down. This is what's called Hertzsprung-Russell diagram. It's really a great little diagram because you see all the suns that are born are on here. Sometimes they're real little, they're called red dwarfs. Sometimes they're pretty big, called blue giants. All right, but they're all of these stars, no matter the littlest one to the biggest one on that spine, are burning hydrogen at its core. All right, but what happens when you run out of hydrogen? You see, when you run out of hydrogen, what's left? Ooh, it's helium. Well, helium takes a whole lot more temperature to burn, maybe about twice as much. So what happens is that a star like our sun, which is right here, a yellow dwarf, what's going to happen to it is that when it runs out of fuel in about another 5 billion years, all right, then it'll just be left with helium. So what's going to happen in gravity, it's going to come down on it. Well, why is gravity coming down on it now? Because the fusion and all that energy is producing a counterbalancing, staying. Oh no, it's not going to let gravity crush me, you see. But if there's no fusion, I'm in cuckoo. So that's what happens. And so as the gas compresses, you know what happens when you compress gas. Well, not that kind of gas. When you compress gas, it gets hot. Okay? And so what happens now is the helium gets hot enough and it starts to burn. But more energy is given out for helium fusion than for hydrogen fusion. So when the sun expands back to, not to where it was, but to something much bigger. So the outside becomes a little cooler and will become what's called a red giant. So in about another 5 billion years or so, we're going to become a red giant, a yellow giant first, and then a red giant. And then what will happen to our planet is, well, we don't want to be around for that. It'll be a little, the oceans might be gone, you know, things like that. It may not be a friendly place to be. So I would recommend somewhere else, though our sun will not explode like a bomb, believe me. It's too little. All right, so I talked about a little bit about star cycles. All the little ones become, the little ones like our sun, what will happen is that after it becomes a red giant, things in the middle is burning helium, but still on the outside shell is burning some hydrogen, and there's all kinds of instability, flow, hydrodynamic instability. So what happens is that the shell separates or divorces itself from the core, and you're left with this ember, this hot ember called a white dwarf, okay? And then the rest of it is called planetary nebula. That's what the fate of our sun is going to be. And planetary nebulas can be pretty. Here's a whole bunch of them. And our sun will probably produce planetary nebula that looks much more like, maybe like this, or that one over there. Not like that bottle, or some of these fancier ones. Because you need another sun to be hooked up to us that affects how that happens. Most of the stars you see, when you go out here tonight or any other night, and you look with your naked eyes, more than half of those stars that you see are two or more stars that are gravitationally bound together. They're called binaries. And so when one dies, the other one has something to say about how that's going to die. And that's why we get some of these weird shapes, because of the magnetic field. All right. So what happens to our star, like this we call it yellow dwarfs? It becomes a yellow giant, like I said. It goes through an interesting period called the pulsating variable, then becomes a red giant, and then a carbon star. And I'm not going to go into these things except that it's destined to become a planetary nebula and a white dwarf, because I want to get to the exoplanets. All right. But look at this. We say, or we think, or we hear in the news that we live on a typical star. our planet, not star, our solar system is that of a typical star. Let me tell you something. There's nothing typical about our sun. Our sun is a yellow dwarf. Here it is, right here. The outer temperature is about 5,800 degrees. It's a whitish star. It looks yellowish because of the atmospheric effects. And look how many of all the main sequence stars that we know about, less than 8% of them are yellow dwarfs. Well, where's most of them? Look at this. The overwhelming majority are these little suckers called red dwarfs. Now don't be mistaken 1 minute. Just because a star is little doesn't mean it's not full of spit and bile like these little red dwarfs are. They're not very friendly they're not very friendly stars. They're constantly doing all kinds of solar storming. They're erupting, emitting a tremendous amount of ultraviolet radiation. So what's the big deal? Because these red dwarfs are so little, they're only like a tenth to a few tenths the size of our own sun, and they're so dim, they're like 1,000 times dimmer than our own sun, and they're smaller. So when you talk about planets, this is a proto-sun, and it looks like most of the proto-suns are going to be red dwarfs, then the planets that form are much closer to the sun. And what we're going to see here in a minute is that we'll have really big planets, like Jupiter's and Neptune's type planets, that are forming in closer to their sun than Mercury is to ours. Oh boy, so this is going to be something wild. That's going to be a very interesting question to address. What happens? What happens? The exosolar systems are indeed very different. I mentioned the binary. I like this cartoon. You have these couple of grasshopper or roaches or something. It's hermit. Daybreak, the sun rises, looking at the beautiful yellow sky, and then, oh, another sun, and one says, look, looks like it's going to be another hot one. And so indeed, it could be rather interesting in a lot of systems with multiple planets. Here's a typical artist rendition of a red dwarf and a planet going around it. It's a pretty picture, so I put it up there. I like the next picture even better. Notice that this red dwarf is not absent. The solar flare, you see that prominence is going up. And there's not too many sunspots in this picture, but there probably should be. What do you mean sunspots? What are sunspots? They look dark because they're cooler areas. But don't be mistaken, these are pretty violent regions. This is where magnetic field, you got to remember, well, maybe not remember, maybe just look for the first time, that the sun is not a solid ball of gas. Well, it's a solid ball of gas, is it? It's not solid. The gas does not rotate as a fixed entity, but rather you'll see one part of the sun is rotating at one speed, another part of the sun is rotating at another speed. The equator is traveling faster than the, no, I got it backwards. I think the pole's spinning faster. In other words, if you were on a gas bubble machine, so to speak, and you're riding around the sun near the top, you'd find that it takes about 30 days to go around. But if you're at the equator, it's a little slower. It takes about 25, 26, 27 days. There's it's called differential rotation. So well, who cares? Oh, we care. Because the magnetic field lines, remember Alfing, those magnetic field lines start getting all bunched up like a string of spaghetti. And you know what happens when you start winding a bunch of spaghetti up with your fork and you're impatient? If you try to eat it, you'll choke on it. But what will end up happening is, especially if you overcook the sucker, is it will start to break. The strands of spaghetti will break. The strands of the magnetic field lines will break. And when they do, and they reconnect, a tremendous amount of energy is given off. You get these flares, and they're associated with these sunspots. So sunspots are important. There should be a lot more sunspots on that picture. Ah, maybe you like this picture. Ha! This artist took my physics class, obviously. You know, because that red dwarf is not a friendly dwarf at all. And this poor sucker over here is not going to be a happy camper. That is to say, any organisms living on it would have to endure some rather hostile environments. Hostile how? Well, let me see what my next slide says. Let me show you. This is an actual image. Actually, it's fairly recent. The star system, Gliese 581, has been known a long time. It has around 5 or so potentially habitable planets, but only really 2 of them are candidates. They're in the Goldilocks, what's called the Goldilocks zone, which maybe we'll have time to see, but I can tell you now. Habitable doesn't mean friendly. Habitable only means temperature is right to have liquid water. And maybe some people are finally realizing you need more than that. So they're thinking along, well, maybe it has an atmosphere and possibly a magnetic field too. Then maybe it'll be habitable. All I know is those are minimum requirements for habitability for us. But then people will point out, well, what about those bacteria living in oxygen, in an anoxic condition under the oceans and horrible conditions, and there's not even lichens down there. They can thrive. There's some extremophile type organisms that can deal with it. But I don't think there's any people like that. Some bacteria. Bacteria are pretty complicated, but not as complicated as people. At least the ones in Washington. But you'll notice something. This is an exaggerated view. This is actually imaging from an infrared telescope out in space. And what we have is, you'll notice that the solar system in the middle is a cartoon. And it's greatly exaggerated. The relative size is really much smaller compared to the dimensions, but it's done for simplicity. Notice we have a ring though. We have something like that too. It's called trans-Neptunian, transuranic, or whatever. It's what we call the Kuiper belt. Okay, where it's a frozen graveyard of what might become comets or what at one time may have been comets. Either way, they have, isn't that interesting? They have it too. So this is really wild. So let me go back. What was I going to say? I'm probably going to say it at one point. I might as well say it now. Let me go back to that picture. This picture here. Because the sky is little and the solar systems are forming tighter in, you can have something the size of Jupiter with only a few million miles from, we're 93 million miles from our sun, but we can talk about something that's only a few million miles, 7 million miles from its red dwarf star. When you get something that close, something magical happens. Magic, it's called physics, but we'll use the word magical. Right? It's the same thing what happens to our moon. Our moon and Earth have an interesting relationship. The official word is tidally locked. And that means the way that the moon, in this case the planet, would rotate, it would rotate in the same rate at which it would orbit. So that what happens is that the same face is always presenting itself to the sun. In this case, we always see the same man in the moon. The woman just got scared of the other side. We always see the same face, or rabbit if you're from the Orient. You know, we always see the same thing. It's been a little bit of jiggle. Same thing with this. The planet would always see the same face of the sun. Now, it's in close. It's in close to a violent sun. It's going to be hot as hell. No pun intended. It's going to be really hot. It's not going to be very friendly. A lot of UV. This planet is partly rotating on its own. So what's going to happen? Its magnetic field may not develop very well because it has to do with the motion of conducting material. That's how we develop our own magnetic field. So you expect a planet like this to have a reduced magnetic field, therefore no protection from the solar wind, the solar tsunamis, okay? And you have the very sharp boundary where it's very hot and very cold. So if there's life, and I imagine there is, Washington level life, you know. If there's life, it will be very primitive. They'll probably live in tidal pools where the temperature ranges won't be quite as extreme. There'll be some help from since the planet isn't spinning much on its axis. What's going to happen is that you'll have tremendous wind gradient, a pressure gradient, that will produce strong winds. Now because we rotate once 1,000 miles an hour, okay, we produce a force, we produce a Coriolis force that helps break up that pressure gradient, and so we get tolerable winds. You know, even if the jet stream is only 100 miles an hour, you know. You go to Jupiter or Neptune, even worse, you're going to have hundreds of miles an hour, and they're way out there. you see? So, you're going to have strong winds that are well over 100 miles an hour, probably a couple 300 mile an hour winds. But the good news about the winds is it can take some of that heated atmosphere and shuttle it to the back or to the hinder parts of the planet. Not enough to warm the whole planet, but certainly enough to increase this terminal region where it might have some really smart bacteria there. I don't know. I think it's possible. Am I scaring you all?
I think I got another class.
Oh, shucks. Okay. I'll give you extra points. So this is the thing about that. Okay, let me move on, and I'll remember. How do we find planets? How do we know we even see planets? There's a couple of cool ways. You can't see them directly because they're kind of small, aren't they? Our nearest star is, besides our sun, which is 93 million miles away, is Alpha Centauri. And that harsh system of hot AB stars or OB stars, I forgot which, would also be a lot more UV. Oh, a very unfriendly environment. So if we travel 4 years at the speed of light to get to a place where we can't hang out, that'd be a terrible waste of time and money. We had to go somewhere else. But then again, Gliese 581, what I just showed you, that's 20 light years. And remember, a light year is pushing 6 trillion miles. So, wow, at the speed of light, it would take 20 years just to get there. And we can't travel at the speed of light. So, you see, most of this may be academic, I don't know. What about time travel? I don't know. You got to be careful about time travel because you might end up killing the person who's going to give birth to you, and you don't want that to happen. You know? So there's a problem with time travel, but there is a way to perhaps go, instead of traveling the regular space line, so to speak, because space might be folded, even maybe possibly through other dimensions, to penetrate interdimensionally, to go from one part of the galaxy to the other.
Like wormholes?
So like a lot of science fiction novels and movies take advantage of it. I don't know about a wormhole, though it's a good conceptualization. There are wormholes, they theoretically exist, but they connect two black holes. And may I tell you, I don't want to be in any black hole. That's what I read. I want to live. So, but the wormholes on television are a different kind of wormholes. They're more like these jump points or it's great for them. I think it's great to think about these things, but there's some serious issues with the physics. But there must be some way, if we're going to ever make any contact with anybody, or then with us, there has to be some kind of interesting way around the problem. I suspect there is, but I don't know. Okay, so how do we find these planets? Well, let me tell you something. Let me show you a picture. See this? No, it's the wrong picture. See this, what you got here, you got what looks like a planet, and it looks like a moon, okay, that's going around that planet. Well, you know what? We say that moon goes around the planet. We say that Earth goes around our sun. We say that Jupiter goes around our sun. And that's approximately correct. It's good enough for government work, but it's not completely accurate. What would be accurate is to say that they revolve around each other. In other words, there's something called a common center of mass, as if it were a balance point, if you wish. Now, for our solar system, that balance point is just barely inside the solar envelope. It's not at the center of the sun, it's to the edge. That means if you're outside looking at our solar system, all right, what you're going to see is you're going to see the sun wobbling. And it's wobbling because of the presence of our planets, in particular Jupiter, but all of them effectively. So, if the sun is wobbling, if a star is wobbling, then we can deduce what kind of wobble, what would produce that kind of wobble, and we can infer. Is that the right word? Guess. We can guess that there's a planet of a certain mass causing that, or a certain minimum mass. All right. This wobbling is a good idea. But how do you see the wobble? If I can't see the planet, how how am I going to see this? I mean, the sun's only a speck of light. I mean, how am I going to see it wobble? Well, physics again comes to the rescue. You know, when you stand at oh, there's got to be a number of places around here where there's no. Okay. I thought I was being yelled at. There's a train. You've been at a train crossing, I'm sure, and I'm sure you've heard the oncoming train. They got to lay on the horn. It's law when they're coming to an intersection. They lay on the horn. If it's going through a small town, they can't travel any faster than 25 miles an hour. Otherwise, they book at 50 or something like that. All right, 25 miles an hour. He lays on the horn a couple hundred feet down the road, down the track. But you're over here sitting patiently or impatiently, and you're listening to this thing. If you're on the train, you're just going to hear, but if you're out here, you're going to hear differently because the pitch changes as it approaches and it departs. Because it's what it's doing to the air, the speed of the air, the speed of the sound in the air, the speed of the train relative to you causes what's called this thing we call Doppler shift. So as it approaches to you, the pitch increases, the frequency increases. And as it leaves you, the pitch decreases or gets more bass-like, okay? Same thing, there's nothing magical about sound. The same thing happens with light. As a light source approaches you, you're going to see a shift in its frequency to the higher energy, to the blue, right? And as it's going away from you, you're going to see a shift in its wavelength too, in its energy, toward the red. So we say if something is moving away, it's red shifted. If it's moving to you, it's blue shifted. So that's how you can tell. What's the sun made out of? Mostly hydrogen, right? Well, you look at your handy-dandy little spectrometer, and you see the hydrogen lines. I see that sucker. Wait a minute, it's shifted. That sucker's moving to me. Oh, wait a minute, now it's going the other way. It's wobbling. So part of the time it's coming towards you, part of the time it's going away from you. So by making note of those changes, then you have an idea of the amount of wobble, and therefore you calculate using sophomore-physics what the mass would be of that planet causing the wobble. That's one way we do it. Another way is with extremely sensitive light detecting equipment. You have a ball of light, and you have a little mosquito, meaning a planet, going across. The mosquito is dark, right? Well, if you can measure really well all the light that's coming off that solar surface, and then when this little speck goes in front of it, what we'll call a planet in transit, then that amount of light is going to drop by a minuscule amount. It's hard to believe, but we can measure that extremely well. So after a number of cycles, yeah, for sure. And so you get an idea for how much light is blocked, and you get an idea for the kind of the size of the planet. So that's another way. And the other way that we do it is we go ahead and send the telescope out in space to get a much better look at these signs. They don't have the interferences of adaptive optics and that. You can get a much better look at all these things. And that's the Kepler mission is all about that. So planets come in all sizes, from itty-bitty ones, but most of the planets we found aren't necessarily bigger because our technology can't find the smaller ones. But don't be deceived. Just because we can't see the smaller ones does not explain easily why we see Jupiter-sized planets in really, really close to their sun. Our Jupiter is nowhere near our sun. It's way out yonder. So, well, why is so many stars that we see have their planets, have their Jupiter-like bodies and so close? That's a good question. Is our solar system truly very different? I like to believe it is, but maybe it's just one part of the grand evolutionary scheme of planets, in that when our solar system formed, there is some thought now, so it's got some merit. It's got some merit. Listen to this. It's possible that our Jupiter, Saturn, Uranus, Neptune type planets initially formed very close to the sun, while we're still in that dusty bubble, right? And then because of the complex gravitational interactions, in fact, it's impossible to solve anything more than a two-body problem, exactly. You can only make guesses because of a thing called chaos. It's a chaos, right? what happens is the planets will migrate. They can migrate, and they can do this fairly quickly. In just a few 100 million years, the Jupiters can be moved from their sun out to where it is now. So, this is an interesting idea that's been forwarded in recent times. And I'm not sure. I like the idea, but I haven't seen the equations yet, the models. But I like the idea because it explains two things we haven't been able to explain so far, and that is there was a tremendous meteoritic bombardment that happened twice. One's called the early, and one's called the late bombardment. And there was a short period of time, lasting maybe 100 million years or so, where everything was just really showered on with a lot of meteor activity. The moon got cratered up to the yin yang, so did the Earth, but most of that evidence has been it's under the water or erased from just erosion and such like that. The moon is a little bit less able to hide the crater, so to speak. But there was two. So what's thought is, what might be thought is, and it's attractive to me, that as these big planets moved or migrated out towards the outer edge to where they are now, then imagine it's like a snowplow pushing snow. You're going to have fallout. You're going to have things falling into the sun. You're going to have things pushed away. All right. So there's going to be an awful lot of the failed planet where our meteor belt is, the asteroid belt is now a failed planet. That's going to be nudged, and it's going to create a bunch of cometary or meteoritic bombardment. But what about the second one? The second one comes from when, as this one model goes, when Uranus and Neptune migrated further out to where they are now, stimulating the Kuiper Belt object. So there was a secondary bombardment, and some people believe, and I don't think it's far-fetched, that especially that last one, may be a result, not the brontosaurus or the patasaurus, or whatever they want to call it now, why we have oil in the ground, not from these dinosaurs, but from a comet delivery system of water and hydrocarbons. Very positive. Some people believe that. It's not completely accepted, but I'm just putting it out there for you to do your own thinking and your own research on that. This is an interesting idea, and it at least demands a piece of fiction, writing a poem or something. At least that it demands. And maybe some serious physics too. All right. Of all the confirmed exoplanets, and there's over 1,000 of them now, according to this cartoon, it's 1,100. I think it's more than that now. You'll see the overwhelming majority of them, 459 of them, as of this date, are Jupiter-sized planets. Wow. Well, I guess it makes sense. You're going to be easier to find the bigger ones, and so that's probably the argument. But we can now see these smaller ones too. So how true is that argument? I don't know. It sounds like maybe there's a lot. Maybe our solar system doesn't have a whole lot of these big planets. We have a couple, 3, 4 of them, but there are some solar systems that have many Jupiters, and some of them are much bigger than ours. So, and they're in close to the sun. So when are they going to migrate? That's what I want to know. I don't know. Okay. Oh, time for a poem. Let me show you something. Remember this picture back here? When in April 2007, I think it was April 2007, there was an announcement, we found Super Earth. Okay? And it was to this star, Gliese rather, 581. It's got 5 planets. I think the one in question was either D or G, I forgot. But it was on the inside part, closer to the part of the Goldilocks zone, where it was believed to be rocky and possibly full of oceans. That immediately spurred this poem, which is not published yet, but it will. Waterworld. On the beach, the daughter squints through a telescope, unveils a million suns sifting through cosmic dust. Her father says, Leodra, there, in the center of our galaxy, see the dazzle of Sagittarius? I heard it on the news today. They found another world like ours. The star near Taurus, they think it has a water world 90 million miles from its sun, its bright yellow sun. Now hurry, we must die. The sun will soon fill the sky with scarlet, and the twilight air is much too thin. The chalky ocean ripples over their smooth arms, thinning the purple depths. So, from the perspective of another intelligent life form on Gliese 581b or whatever, the sun would not be coming up, and I'm putting them in the tidal pool here. The sun doesn't rise and set because they're tidally locked. Now, since that announcement, the amateur optical astronomers said, wait a minute, you guys are wrong. You guys being the professionals. You guys are wrong. This planet, from our measurements, is not in the Goldilocks zone. It's much too close to the sun. It would be a hot, barren place. And the professional radio astronomers concurred. I think it's great when amateurs and professionals can work together like that. I only wish that the same level of cooperation existed among amateur radio astronomers with the professional community. But I'm working on it. Okay, so all this talk about planets and life promotes the question about the quest for life. I mean, we want to know, are we alone? And what would they be like? And I put in here, not as a joke, maybe it's sincere, because it really, I'm not a philosopher, but you know, maybe there's something called exosociology, you know, we really want companionship of others who share our universe, you know. It makes sense to me. Right now, I'm not much in the mood of hugging any bacteria. It's just an interesting idea. Just recently, I mean, like a week or so ago, they imaged, the professional astronomers imaged, no, they didn't image, I'm sorry. They with their highly sensitive, brand new, not fully yet commissioned radio telescope in Chile. The ALMA telescope is so much more sensitive that it can zoom in on, not zoom in like it's looking at a picture, but zoom in on in the sense of being able to detect the spectroscopic signatures of various molecules and atoms, or molecules in particular. Here, they were able to, with such great resolution, they were able to tell about these chemicals. Oh, we talked, no I didn't. I'm going to talk about it in a minute. This is what I want. This is the picture I want to show you. Chemistry is my first love. But though it's not organic, I'm a physical theoretical chemist, but nevertheless I can get excited by organic molecules too, I really can. And this guy here, cyclopropylenolidine, it looks, if anybody who studied chemistry knows, you have a 3-carbon, in a 3-carbon ring, and you won't be too happy. It's highly strained. In fact, you're not going to find this sucker on Earth. Much too warm. But in the cold places of like, I don't know, 30, 40, 50 degrees Kelvin or less, this sucker can exist. Unstable, but it can exist. It was this guy that they saw a lot of right here on this edge, but none right here on this edge. You can tell that by looking at the spectrum of that molecule. It's so cool. And there's a bunch of people who calculate what the spectrum would look like of stuff that we have yet to make on Earth that might exist out there. That's kind of interesting too. Chemical physics, physical chemistry, kind of stuff. It's kind of weird. There's something else here too. It's sulfur oxide. Over here, there are crystals. I'm sorry, yeah. Over here is a crystal. A solid crystal. It's that cold. But right in here, it sublimates, becomes a gas. and its signature is gone. Woo! What's going on right here? What's going on? This is an artist image. It's still pretty dusty, as you can see. This protoplit of the solar system is in the process of being formed. This is what's called, or what they call, a centrifugal barrier. Even though we teach our students never to use that centrifugal word. Here we go, see, it's the professional community. So I'm forced to use it too. Centrifugal barrier. Basically, the stuff is spinning so fast over here that gravity can't, matter doesn't fall in. Matter doesn't fall in anymore. It's basically it's an inertial barrier of sorts. Is what it really is. Okay, so this dust doesn't fall into the star anymore. In the centrifugal barrier, there's about a 50 degree or 30 degree, I forgot what it was, temperature difference, because as you pile up things against each other, you're going to get a little heating. And that little heating is what makes these changes and also help identify exactly where these barriers are. That's kind of really cool, especially since it's brand new information. All right, so why is, here it is, it went from 30 degrees Kelvin to 60 degrees Kelvin, 30 degree jump. So the molecular cloud was around 30 degrees, maybe a little cooler than that to start with, not much. So you see, as that goes lost at 10 degrees before, and this is probably starting to heat up a little bit. Actually, I would have thought it would be a little warmer by now, but that's okay. The funny thing about this particular substance is that, besides begging the question of other fancy molecules out in space that I might want to spend any time on, because time is running. I'll come back to this if we need to. What's really cool about this chemical, first of all, there's a lot of it. A lot of the C3H2 stuff? Why? I don't have an answer to that one. I wish I knew. But, okay, for however reason it forms so much, it is now known that it's an important precursor to what's called polyaromatic hydrocarbons. These form on the grains in interstellar dust and are enormously important for the possibility for the building blocks of life to have originated not on the planets, but in outer space. Why? Let's see if I say it. Let's talk a little bit about carbon chemistry. Carbon is really wild. I might come back to that picture. I want to go to this picture. I want to go to the periodic table for a minute. You know, the periodic table of elements are arranged by mentally in what's called groups. The vertical columns are groups. And the thing about groups is the outer electron configurations are very similar. Okay, in fact, they're the same. I mean, the atom may be bigger or smaller as they're filled, but to the outside world, it looks the same. So you'd expect the chemistry as well as the physical properties of the outer elements of the elements of the group to be the same. And in general, that's kind of fairly true. But there's a problem. Not a problem. There's something particularly unique about this group 4, starting with carbon. You have carbon, which stands out on its own. Then you have silicon and germanium, which kind of like are similar. Then you have tin and lead, which are even more dissimilar. Okay, you go from something that's completely non-metallic to something that's completely metallic. It's a very strange group. And even though the outer electron configuration is the same, they all don't behave the same. Very, very different. And the thing that I like about carbon that makes it special over any other element on this table is its ability to mix its own atomic orbitals so that it now can produce a multitude of bonding opportunities. Wow. What do you mean by that? Look, let me show you this picture. Here's just a few of the simple orbitals. They look like, you know, big old sphere, or these are regions in space where the electron most likely resides in. Some dumbbell shaped and some spherical. And there's some other ones too, of course. But look, you can start mixing these orbitals so that you form different kinds of bonding opportunities. I'm repeating myself, but it's worth repeating. And it's because of this property that we have a whole branch of chemistry called organic chemistry. The ability for carbon to do this is unsurpassed. Silicon can do it a little bit. You can form some interesting polymers and stuff with silicon. But you're not going to form complex organisms like a bacteria, let alone us, based on silicon. It makes great science fiction, the Sandman, you know. Great science fiction, but that's where it stops. And any other element's even worse, including phosphorus. So this thing called hybridization is really, really important. All right. Molecules in space. I think one of the first ones discovered was a simple molecule called formaldehyde. You know, the sticky stuff in the biology lab. That formaldehyde is kind of cool. The thing about formaldehyde is that it helps it combines with other things to produce stuff that have become important for biochemicals. Like there's ammonia and carbon dioxide, carbon monoxide, formaldehyde now, of course hydrogen, plenty of that, water vapor, those things can all combine with the help of ultraviolet light, for example, that will create free radicals for each combination. That's how you form these complicated things. Out in cold space, it isn't going to be a thermal reaction, it's going to be cold. So it's mostly because the light breaks in bonds, forms free radicals, and recombine them. It takes a long time, but they'll do it. And so otherwise unstable molecules can form. All right? And so that brings us to the simplest amino acid, which is the building block of DNA, okay? Part of the essential part of DNA, that we found, not me personally, but we found through radio observation, interestingly enough, glycine out in outer space. And so this is really cool. Now that brings me to the question of this famously touted experiment. I'm going to tell you something right now. I'm not a proponent of Miller-Urey, okay? And for the reason I'll tell you here in a second, if you read faster than I will know. But Miller-Urey, back in 1952, if I recall correctly, in Chicago, great city, great people, good pizza. Bad experiment. But it was a good idea. It was a great idea. It was a beautiful idea. And in fact, I loved the idea so much that I believed it for years until I got into my advanced organic chemistry class at Loyola College, now the Loyola University. And they told me it's not possible for it to be the basis of life. Well, what was so great about this experiment is that they took what they thought were the primordial ingredients, the atmospheric composition of the primordial Earth. Ammonia, carbon dioxide, water vapor, mainly those guys. Maybe some sulfur stuff too, I don't know. But those guys mostly. And then it was believed that with the electrical discharges, you form these free radicals, they combine to form amino acids. And sure enough, they did the simulation in the laboratory, and they found amino acids. Hallelujah, I love it, I love it. Now, how do you go from amino acid to DNA to a bacteria to us is another question altogether. But the idea that you could form, this sounds great, sounds exciting. But then I learned something about stereochemistry, and it has nothing to do with sound. I learned something about stereochemistry when I was taking organic. I guess I wasn't paying attention in my sophomore organic too well, because it didn't hit me the importance of, we have a fancy word for stereochemistry. We call it chirality. Let me show you a picture. There. We have left-handed molecules, and we have right-handed molecules. And never the twain shall meet. We are made up all of left-handed amino acids. The problem with the Miller-Urey experiment is that it produces both left and right-handed amino acids. So I said, okay, well, so what? The so what part is like throwing a monkey wrench in machinery. It won't let the others, they'll get in the way. And they won't let the proper RNA strand or whatever is formed. Because once you get to that DNA part, if you unzip DNA, and this is done in a lab, you can do it today in a biochemistry lab, you can unzip DNA, right? Put them back, throw them together in solution, and the miracle of self-assembly, they'll zip back together again. It's incredible. It's truly a miracle. But it's possible only if it's chiral, if it's pure. You cannot do this. This DNA will not develop, will not self-assemble with a racemic mixture of these amino acids. So that theory, as much as we liked it, had to go by the farm. It didn't like it. There has to be another way that produces either all right hand or all left hand, but not both at the same time. Free radical mechanisms, as far as I can tell as a chemist, take off my physics hat, and I'm looking at these molecules and I'm just ripping off, photolytically breaking the bonds to leave these free radicals. I think it's even more indiscriminate to form chirally pure mixtures in a free radical mechanism, which is more likely in outer space. So there's got to be something. There's got to be something else going on. I don't know what it is, but this much I'll tell you. This is exciting. I just learned about this from Dr. Miguel Fuentes Cabrera, who worked on the RNA world theory at Oak Ridge National Labs. He was one of the featured speakers here at Anderson's on the VP. I get to invite all the speakers. It's kind of cool. So I was listening to him, hoping I was able to bring something to this lecture. If I could learn from him, I wanted an answer to that question. He couldn't answer it, of course. He couldn't answer it. But what he was able to tell me was this. If you have the RNA to start with, which came first, the protein or the DNA? Maybe an RNA molecule like it, but still forming the RNA is still a magic question. But if you have something that does both functions, a supermolecule of sorts, then what's really cool about the RNA is that the self-replication, or self-assembly rather, will happen if you put it on the right kind of substrate, like borates, silicates, or even metal surfaces. And they'll organize themselves into very specific patterns. You can make anything, and this is actually a product of nanotechnology, that we're trying to, by just strictly the self-assembly, even synthetic type of DNAs, the kinds that wouldn't support life. Very fascinating how you can just create anything. So I got the idea that maybe there's a substrate, a particular mineral, that would be discriminating of the left and right-handed ones. I'm thinking like science fiction more than as a physicist, or chemist. I'm thinking maybe there's a way that the stereochemistry is you can selectively collect all the left-handed in one and all the right-handed in the other. I don't know. Right now, my guess is as good as yours. Yours is better than mine. But there's got to be something, and it isn't just pure chemistry. It's not a reaction mechanism that I can tell. Really, really important. All right, I'm going to move on. These grains. I mentioned the PAHs before. It's just the important thing is to realize that you got these complicated organic molecules in these silver grains. They get exposed to light, and a bunch of reactions can happen, producing organic chemicals like methanol and ethanol and ammonia and a bunch of other goodies, and those complicated substances from them. But here's the thing: it's really exciting. Again, who would have figured something this complicated would be so common in outer space? When I was a sophomore in college taking organic chemistry, Smith and Crystal was the text I used. I don't think you'll find it anywhere. It was so hard, I think somebody burned it. That was back in the days when mechanisms was a new thing. And organic chemistry was taught by systematic function. You just study each group of things systematically, and then you realize that there's a pattern. Since then, we teach organic chemistry. Notice a similarity between an organic acid, an ester, and aldehyde. You see, they all behave this way to this kind of reagent. This is why. You look at how the electrons attack and how they move bonds and how they break and form bonds. It's a mechanistic approach. So you can't memorize. You got to understand. That's cool. That's what I was having. So Dr. Zazek said, and if you think you're going to pass this course with just memorization, well, I got news for you. You'd be lucky to get a D. So I did well, but I remember I almost failed because this particular chemical, hexamethylene tetramine, this is a horrible thing for any professor to do to his student. But I think I was one of his favorite people to pick on. So he gave me this as an unknown. And there's a long story behind it. I got it right, but it's a very peculiar compound. And let me show you this other picture. You can see this is just That was mean to give me that. That was just downright mean. But he did. And I got it right. So who cares? Aha! Hexamethylene tetramine mixed in acidified water produces amino acids. That's why we care. We care about it because there's a lot of this stuff in outer space. Why? I don't know. Why would that form? Look, I'll have to ask the Lord that one. But this is ubiquitous, just like another crazy 3-ring compound was that produces the initial ingredients, I guess. But you can form amino acids, and it's been duplicated in the laboratory. Are they chiral? They're probably still receiving mixtures too, I imagine. Okay, so that ends my discussion, as you see, which was most of it, on exoplanets and life, the whole 9 yards. You all sat so quietly and patiently without asking me questions. Either I hope I didn't make you scared to ask me something. Now I got more stuff to talk about, but it's another topic. So before I move on, in what time I have left, do you want to ask me anything about this stuff? And I'll promise I'll try to.
On the Kepler planets, there's the 10B, the 11B, and the Earth is in between the sizes. Why is that?
Oh, the ones that were found? I don't remember. Let me see. This one? Oh, Earth was put there as a matter of scale.
Okay.
You know, we're not self-detecting. Okay. Yeah, it was just showing you that the smallest one was Kepler 10 Bravo. That's the smallest one we found so far. Okay. And maybe these numbers have changed too since this slide was made, which wasn't that long ago, but things are happening so fast. You know, discovery the data so much more frequently now. It's just an incredible number. But remember, most of these planets belong to red dwarfs. Not exactly friendly. And what about in binaries too? I mean, you worry about orbital stability. Though you can, there are models, there are papers out there that you can have a planet orbiting both suns. I don't know how friendly of an environment that would be. It sounds like it would be pretty cold to me, but all right, you can have a stable orbit around both suns. You can have them between the suns. You can have them even shuttling both suns. I don't know. All I know is that if we move, if you only move a million miles sounds like a lot. Let me tell you, it's nothing. We're 93 million miles from the sun. So what if we just moved in 1% closer or 1% further out? 1 million miles. Either way, it should be any big deal, right? We would not live. We would either roast or we would freeze. We are so fragile. Anyway, I know, we're not bacteria. I understand. I hope I answered your question. I'm losing most of my audience.
Yeah, it's just another class time.
Oh, okay. But I got you all counted, right? I want to show you something really cool. I can do this. I think I can do this now. Black holes. This is another really popular topic. And, you know, there's so much we don't know. And apparently Dr. Hawking doesn't know either. Because he's being poo-pooed by the professional community right now too for him saying, well, there ain't no event horizon, trying to play both ends of the stick. And he's got a lot of flack for that. And I agree with his opposition. No, they have event horizons. There's just too much good physics to show otherwise. But here's an interesting picture. It's an artist picture, I think. Yeah, I'm sure it is. Of a galaxy with the jets of emitting material from the event horizon edge to outer space. I mean, so matter inside the event horizon, nothing can get out. But right there, that boundary, it matters falling into the black hole. Right there at the edge of the event horizon, the materials can be converted into and produce these extremely long jets, light years, many tens of light years, hundreds of light years long. I mean, Can you imagine the physics, the hydrodynamic stability of a jet maintaining its structure that far away? It's a tremendous interplay of electrical and magnetic fields that are causing. I mean, how? Nobody knows exactly why. I mean, such a beautiful jet, so long. I mean, some self-limiting, self-regulating thing is going on. Something is going on. It's just wild. I don't understand it. But how do we know that they're even out there, these black holes? Well, there's several, like most things in science, that you can't see directly. You look for the circumstantial evidence. And circumstantial evidence is not a dirty word. Actually, as somebody who I read a book about, a lawyer talking about, he used to write a legal column for the Chicago Tribune, was making an argument about circumstantial evidence versus direct evidence. And he said that direct evidence can always be challenged. But circumstantial evidence has no agenda. So if you have enough circumstantial evidence, the conclusion, as Sherlock Holmes would put it, inescapable. This is the case with the black holes. You can't see them, but the information is inescapable. And these are the three ways. And these are kind of cool. You look for weird motions around some object that you can't see, and if you look with a radio telescope, because you can't do it with an optical telescope, or an infrared telescope, to the center of our galaxy, so you can image the stars, and you watch their motion over time, you're going to find some really strange stuff. And this is the strange stuff that you're going to see. Notice the time scale here is not minutes or years, well, they are years. Okay, 1992 to 2006 or so, okay? And you'll also notice, well, that's the most important thing to notice. Some weird motion going on at some unknown center that you can't see. You also will see some, again in the radio, Sagittarius A star is the radio telescope center of, the radio center of our galaxy. And you'll see this dark area that suddenly brightens, okay? Notice the time scale now is in the order of tens of minutes, okay? And the distance is in the order of, I mean, you can, for a matter of scale, I mean, remember, a light day is a distance that light travels in one day. At 186,000 miles per second. How many seconds in a day, you know? It's a lot of seconds. So it's a pretty, I mean, this thing looks like a diameter. This looks like about a light, I don't know, light day or like 2 light hours. It's a pretty big distance is what I'm getting at over a pretty short time. So matter seems to be falling in that's now emitting the radio as it gets excited. And that's one way. So the other way is just watching glowing jets coming out of matter. Again, notice the scale. This object is 40,000 light years away, and yet, and you can see the vertical scale. I think the whole thing is like 30 light days. So these are pretty huge jets, right? So these are the kinds of things that tells us. And one of the things that I like to do with my class is this is a near infrared image of the center of our galaxy. And if you were to image with the infrared the center of our galaxy, because you can't do it with visible, like I said, down here in Hawaii, we were able to do this, you're going to get pictures like this. Well, what you get is, you get these weird motions, right? The trick is, to make it a practical experiment, is to take, can you see it? Let me see. S20, it's hard to see. But see the strand here of this particular strand, the different colors for each year. I mean, different shades of one color for each year. And there's data going from all over this 8-year period for this particular image. But you can see it. If you could look at this closely, you'd see a nearly circular, nearly head-on image of what looks like the orbit of this star. Okay, so the star. You see other stars that are having much more weird orbits. Okay, but this one in particular, we're able to see face on, and that's important because it makes the calculations really easy. What I have my students do is to go ahead and try to determine the rest of the orbit, measure it from the center, the size of the orbit, and also how long it takes. You can do that with simple geometry. Well, if it goes from here to here in so many years, and to go around, you know the rest of it. So you know the period, and you know the distance, and you know the orbital radius, right? From just measuring. The only thing else you need to know is what scale. I mean, I want real numbers. Well, Keck tells us that that little size of the arrow is 2/10 of an arc second. All right, so coupled with that information and a little bit of, where's that picture I'm looking for? Oh, there. With that picture, knowing where we are, all right, here's the orbital radius that you can measure in terms of angle, all right? You want to convert that into a distance, so you just apply what we've learned in grade school, the central angle theorem. It's like I do. Convert this angular measure into a real distance, all right? Comes out to be about a light year. This is about a light year, all right? Then you can calculate with sophomore physics. Nothing more. You don't need anything more sophomore physics. What do you mean? Look, all you need is the balance of force. Do a free body diagram on a star orbiting this unknown center. Call it a black hole for now, with a certain mass. All right? The gravitational pull of that black hole on the star is counterbalanced by the centripetal force, mv squared over r. You set them equal to each other, you solve the equation, and you can get the mass of the black hole, this central body. All you need to know is capital T, which is the period, and A, which is the orbital radius. Actually, same major axis. Okay, so, and if you do that, and I'm not going to have you suffer through, I'm not going to have you suffer through my calculations. I'm just going to get to the bottom line, because the best is just geometry and stuff like that. What do you get? Hold on, where's the number? There it is. What do I get? I mean, this is actual stuff. I got, using that picture, and my students hopefully will get something very similar, almost 4 million solar masses. That's how big our black hole is. Our black hole has the mass of 4 million of our suns. Now, it's got a big accuracy error because it's a sloppy technique. But just like when you go duck hunting with a shotgun, you're an awful big spread of bullets, but you know, you're bringing home supper. So you're accurate. Maybe imprecise, but you're accurate. It's an excellent example of that exercise as well. And that's all I want to say about black holes in that respect. But do notice that our Milky Way is no longer the way that we used to think about it. It's got, the center now is considered very elongated. It's actually called a barred spiral. It also has a lot of stars. I grew up with a number like 100,000 stars. The estimates these days are at least 200. No, not 200. I'd say 100,000. I didn't mean to say 100,000. I meant to say 100 billion. The estimates today are at least 200 billion, and some of them even put it at 500 billion stars. We have a large galaxy. It's a beautiful galaxy. And this is probably the close to what it really looks like in any other picture you may have seen in your life. This picture right here is very, very similar, we believe, to what our galaxy looks like. And it took radio astronomy to determine that we have these spiral arms. It's really, really cool because of the motion of gases. And being hydrogen being the gas, and we can see hydrogen real well with a radio telescope. We can put together the puzzle and come up with a structure like that, even though we're way out on one of these arms. That's really cool. All by itself is magic. All right. So that's it for the black holes. And if you have any questions about the black holes, I know I could have talked a whole lot more about black holes. I thought you just wanted to hear about exoplanets more than you did about black holes.
John,
yes.
Yeah. What's your best estimate on sort of the state of our technology and its development until atmospheres of Earth-sized planets are going to be able to be characterized? What's your estimate?
A couple of years.
Yeah.
The most. We're really, it's really somewhere remarkable advances have been made. And our ability to see smaller and smaller planets, to see Earth-sized planets, is incipient. And now, with ALMA, I don't know if anybody's talking about it, but, you know, well, maybe it's not quite a thing for ALMA, because atmospheres, that's another issue. That's planetary atmospheres from that far away. I mean, that may be a little tough. But we can learn enough. I mean, in our own solar system, you can look at the light reflected off of an atmosphere of one of the planets, and through spectroscopy, you can learn an awful lot about the composition, or by these flyby satellite probes. You know, like we know, for example, that what's that? Europa, a moon of Jupiter. Because of looking at the surface reflected spectroscopy, we can tell that particular salt deposits are very much marine-like in nature. And by the wobble induced in the spacecraft, you can deduce that it has a subterranean, subsurface ocean. And the density information even suggests a saltwater ocean. That's consistent with the mineral deposits that were found on the surface. So that kind of technology is very exciting, and we'll learn probably a lot more about our own solar system in the next few years. I mean, what's her name? Oh gosh, it's on the tip of my tongue. But she's in charge of that Saturn imaging project. Tremendous work that's coming out of that group. Finding moons and Enceladus with ice, water ice, volcanoes, finding all kinds of Titan is a hostile moon of Saturn, which rains methane and ethane. I wrote a poem about that called Hard Rain. I imagine an intelligent life form that came out of the diesel pools, and they're having some marital difficulties. And here in the middle of a potential extinction level event. Why? Because the shift was happening in the global weather on Titan, where the tropical rains are starting to move up. These are rains of methane now. We're starting to move from the equator to the poles. And I just imagined what I knew as a physical chemist about a dielectric liquid like methane. What happens, and you really worry about this when you're in a gas station pumping gas into your car, another dielectric liquid. You worry about static charge being built up on the conduit, okay, and being made a lot of organoplastics. And I'm thinking to myself, with the sloshing, with the deluge of rain and the flow of rivers along these plastic-like banks, I can just see all kinds of charge building up. And then if there's an electrical storm, boom, end of life. You know, it's just poetry. It's just science fiction. But you know, it's interesting to think that we don't appreciate how fragile we are in our own world, let alone these other really hostile environments. That maybe bacteria could exist, but I have a feeling they may have a hard time with something like that too. I don't know. So anyway, I hope I answered your question a little bit.
You did. Thanks.
Yeah.
Would you like to wrap up with one of your poems?
I surely can. I surely can. Let me see. Okay. I suppose you want an astronomy related. How about, well, this one isn't published yet, but this is timely, since I've worked on Voyager. That was one of my claims to fame, is when I was a research chemist for Mark Marietta back earlier in my life. I worked on the Viking probe for the light detection on Mars, and on the electroexplosives that went on Voyager probe that jettisoned the doors so that the instruments could be exposed when they were outside the danger of the radiation fields. And right now, so it does my heart so good. Just one of the Voyagers just left our solar system, and the other one's not too far behind. It's what, 14 billion miles out. So I wrote a poem called Voyager not too long ago. And I think it's in pretty good shape, and I'm just trying to find it. So now I'm going to order Voyager. There it is. And I guess I'll read it. And you can tell when I wrote it because I wrote it actually a few days after this, because the epigraph reads, Voyager. On August 25, 2013, the spacecraft Voyager 1 left the heliopause for interstellar space. Now a wanderer between stars, freed from hold of gravity, free to sift stardust in outer space, free to touch the face of God. Heat of its heart, a nuclear battery, keeps it warm enough to call me home from 12 billion miles out. Solar wind to its back, fading after turbulence in the crossing. It searches for answers, but only finds more questions. The whole host of heaven smiles, and I stand on the precipice of the universe to catch that faint glint, that last static hiss of its cry, the silver thread of my soul tingling with starlight. A rocket blast in my youth rattles the shards of memory. Looking back, only a smattering of planets, bone-white specks in the glare of a dimming sun.
Thank you very much, John.
Thank you.